Hi, my name is Oscar Gomez, and I will give you an overview of SASM. SASM is an acronym for Super ASM, making reference at the power and flexibility of SASM over conventional assembler. Okay, so let's talk a bit about SASM main features. The first and most important feature of SASM is its friendly syntax. Friendly syntax comes from the fact that SASM uses infix notation for most operators, whereas classic assembler uses a prefix notation. The second main feature of SASM is its high flexibility, which also gives it a lot of power. The flexibility comes from two facts. The first one is the fact that operators can be used as operands or another operator. The second fact is that some constructs, as the assignation and conditional, are treated as operators, so they return a value when executed. This allows the user to do clever things when coding. A third feature of SASM is the use of an evaluated values stack. This stack keeps track of the result of the last evaluated expressions, so they can easily be referenced by using a keyword. This allows the user doing tricks such as passing arguments in an indirect way to a subroutine call. The SASM simulator is a simple tool that allows the creation and testing of SASM code. Being a simple tool makes it very easy to use. It has a watchdog timer to avoid infinite loops, and it also has implemented a real-time code formatting system which highlights with colors the code as the user is writing it. Okay, now I will give you a brief overview of the general architecture of the SASM processor. The first thing I will talk about is the capability of using operators as operands. In classic assembler, an operator may use only fixed values such as integers and memory addresses as operands. In SASM, on the other hand, an operator may use values as operands, but also may use other operators as operands, which at the same time may use both operators and values as operands. So let's consider an example. In classic assembler, the addition operator may only receive as operands fixed values such as integers, memory addresses, or register names. In this case, for example, the addition operator has a 5 and a 3 as operands and produces the 5 plus 3 shown expression. In SASM, on the other hand, an additional arithmetic operator may have a 10 as an operand, but also may have another additional operator as operand, which in turn may have an 8 and a 7 as operands. All of these will produce the 8 plus 7 plus 10 expression. Of course, even more complex expressions can be created by mixing different operators as needed. In this example, two different arithmetic operators and an assignational one are used for producing the shown expression. Working with memory is very easy with SASM. There is only one memory bank in the processor, containing 1015 16-bit registers. Each one of those registers has a unique address for being referenced when coding. Such reference can be easily made by using the square brackets operator. The square brackets operator, in fact, references the value stored at the memory position told by its unique operand. For example, a 5 between square brackets refers to memory register number 5. Of course, Expressions can be put inside the square brackets to refer a desired memory register position. The SASM simulator user interface is really simple and easy to use. Here we can find the menu bar, which has three items. The first one, File, brings the user the possibilities for saving and loading his work. The second item, Simulation, brings the user some tools for compiling and running his code. Finally, the third item, Options, pops up a window for changing some simulator options. The white zone is the place where the user can write his code. This table is the place where the values stored in every processor register are shown. Finally, these buttons bring the user the same functionality brought by the simulation menu items. Okay, so let's write some sample code. As you can see, code is automatically formatted as it gets written. For example, operators are marked with a red color, whereas statements are marked with blue. After writing the code, the simulate control can be used to compile the code, and the step 1 control can be used to run one line of code at a time. The running line is highlighted in the code. The memory grid shows every change in memory as soon as it is made. The run control can be used to run all the code at once until the end of the program. The simulator uses a watchdog timer for avoiding infinite loops. The watchdog timer can be configured in the Options menu. There you can put a value in seconds for the watchdog timer to raise. For disabling it, you can use a very high value as 5000. In this case, we will use a 3 seconds watchdog timer to see its effect. So let's consider that we create an infinite loop. If the code is run step by step, there will be no problem, as the user still has the control over the simulation. On the other hand, if a user runs in continuous mode a program with an infinite loop on it, he will not be able to regain the control of the program. In this case, however, the watchdog timer will raise and terminate the simulation, allowing the user to check and correct the problem.